Welcome back to our quantum key distribution series. It's great to have you here for the second lecture. In our last session, we laid the groundwork by introducing QKD, the basic mathematical notations, and the notion of qubits. We explored how quantum states are represented using the powerful bracket notation. Today, we are going to build on the foundation by discussing some essential concepts that will be instrumental for understanding QKD protocols. We will dive into multiple qubits, explore the fascinating tensor product that combines quantum states, and touch upon simple quantum measurements to see how we extract information from these states. These concepts form the backbone of quantum information. For instance, understanding how to work with multiple qubits is crucial for describing entangled states, which are key to secure communication in QKD. By the end of this lecture, you will have a clear grasp of how to describe multiple qubit systems mathematically and how measurements reveal quantum information. So let's start with the concept of multiple qubits. So we have a concept that we could write the classical bits in the form of a bit string. So consider we have classical 2-bit string of 00 or 01. So our goal is to write the 2-qubit state from the intuition of the classical 2-bit string. So as in the single qubit state formalism, we could designate the 2-bit string, a vector, and we can get a 2-qubit state. So consider we have a 2-bit string and in the form of a binary bits 0 and 1, and we could have four four possible 2-bit strings like 0001 and 10 and 11. So let's denote each bit string with a four-dimensional vector. So consider we have 00. We could denote it as a classical vector, and we will describing with a bracket notation. So we have 00 uh, state vector, and it in the column vector form it can be described a four-dimensional vector 1000. Similarly, 01 can be described as state vector 01, and in the column vector form it can be described as 0100. Similarly, 10 can be described as a column vector 0010, and similarly for 11. So state vector would be a linear combination or superposed state of these basis vectors. And these state vectors that we are defined classically are form the basis of four-dimensional complex vector space. So any qubit vector or 2-qubit state can be written as the linear combination of these basis vectors. And this could vary uh, with the help of these complex amplitudes. So, for example, I have a state that has equal amount of these basis vectors, and each complex vector has a value of 1/2. So there's sum of the square of the complex amplitudes would be 1 for this vector, and this vector is a normalized vector. Similarly, we have a very special vector that we are going to see in our QKD protocol is an EPR state. And it is also a superposed state of 2-qubit vector, and it has a complex vector amplitudes of 1/square root 2. And it is also a normalized vector, and it can be checked by the inner product and taking the square modulus of it. So it is a convenient way to describe two qubit state, but uh, there is a more general concept to write the n qubit state. Uh, and it is a tensor product form. And in tensor product formalism, it is quite convenient to write the joint state of these vectors. So consider we have states psi A, and it is an element of state vector of a vector space of dimension 2, and similarly psi B, and it is also state an element of the state vector of state space of dimension 2, and we want to write their joint state. And how can we write these joint state? And this could be done by a tensor product formalism. So, for example, and it could be defined by a simple example. So we have a psi vector, psi A vector, which is a superposed state of 0 and 1 with complex amplitudes alpha A and beta A, and we could write it in the column vector form. Similarly, we have phi B vector, and it could be written as the superposed state of 0 and 1, and we have a complex amplitude alpha beta, alpha B and beta B, and it can also be written as the column vector form. So tensor product gives us the joint state of these two different states, and from two different elements of two different Hilbert spaces. So consider we have state psi A, and it is a and it is with it is associated with Alice setup and phi p, and it is associated with the Bob's setup. So it can be described by a joint state with the help of tensor product. So we could write the tensor product of psi A and phi B in that form. Sorry, it should be psi. It should be phi in rather than the psi. It is a typo mistake. So we could write the tensor product in that form, and it is just a multiplication of these two vectors. And it is quite a special multiplication, as it increases the dimension of the resulting state vector or resulting joint state vector. So we start with a two-dimensional vector, and we end up with a four-dimensional vector. So it doubles the dimension of the vector. It doubles the it doubles the dimension of the vector with uh, so it doubles the dimension of the vector from which we originally started. So we originally started from a two-dimensional vector. The resulting vector or the joint vector is the four-dimensional vector. So it is a very nice and concrete concept or to write the joint state if we know the individual state vectors. So there is a convention to simplify the s- the tensor product on paper. So we have the tensor product between the two states, and we could write without the symbol of state vector or without the symbol of a tensor product. Similarly, the tensor product between 0, 0 state can be written as the 0, 0 in the single cat notation. And if we have the tensor product between n numbers of similar states, we could describe in that form as the power of the tensor product with n showing the number of state vectors that are multiplying with each other. So tensor product has very nice properties, as it is distributive, as we can see that the multiplication of vectors, multiplication of or the tensor product of a state vector psi1 with the state vector with the sum of the state vectors in parentheses can be written as this, and they are both equal. And it is also associative, as parentheses does not affect the overall tensor product of these state vectors. And in general, the tensor product is non-commutative, So get if we multiply the state vectors as this in psi1 and in this order, as we multiply these state vectors, it is generally not equal when we flip the order of these state vectors. So in general, it is non-commutative. So there is a very nice application of the tensor product, as we could build basis uh, from a single qubit state. So we have the one of the basis of four-dimensional vector space. We could construct it, as we see in multiple qubit concepts. We could build this from single state vectors with the help of tensor product. So this basis state of four-dimensional vector space could be derived with the tensor product of two state vectors of two-dimensional vector, and we can end up with the same results. So it is a very nice application, so that can be used to build n-qubit state with the help of the tensor product. So we have seen that how to write the multiple qubits and how to write the multiple qubits with the help of tensor product. So we have a concept of measurement in classical world, as we could denote the presence of light with the bit 1 and absence of light with the bit 0. So how could we see, or how could we map this concept into our qubit or quantum framework? So measuring measuring psi uh, could give us the state 0 or state 1. But the state's vector psi is quite different from our classical intuition. It is neither in state 0 or in state 1. It is a superposition of state 0 and state 1. So how can we answer this type of question? So the simple and very elegant way of countering this kind of question is the formulas of quantum measurement. And quantum measurement has a beautiful or quite important aspects, that it is probabilistic, and it perturbs the state that we are measuring. So we want to know that how much state 0 is in state psi. So it could be obtained by inner product of state psi with state 0, and we get the modulus square of modulus square of the amplitude, complex amplitude associated with the state vector 0. And similarly, we could get the probability of getting outcome 1 or state vector 1, and we get that it is just the modulus square of the amplitudes, complex amplitude associated with the state vector 1. So it gives us the nice interpretation of these complex amplitudes as the probability in our physical interpretation. So the complex amplitude square of the sum of the complex amplitude squares of these should be equal to 1, and this gives us the uh, idea of that the probabilities should be summed to 1, as it is the usual case in our statistical analysis. So there is a wonderful application of the measurement, as we know that we could build computers, and we could uh, draw the randomness from these computers. And this randomness is usually very helpful in applications like games. So there is a notion that the randomness derived from these computers is not a true randomness, as it is based on the algorithms. And algorithms are human made, and anyone who knows the algorithm can infer that the randomness are not true random. The randomness derived from these computers are not true randomness, rather that it is just our just a part of our ignorance, or the uh, person's ignorance who do not know the exact algorithm. So there is a very nice way to use the concept of measurement to uh, get the true randomness from some kind of physical process. So we deterministically prepare a state as such, as the superposed state of 0 and 1, and we apply the standard the measurement in standard basis, and we get the bits random bits of 0 and 1 uh, on the basis of these measurement. As there is an equal chance of getting 0 and 1 by measuring in them standard basis, we get a true random numbers. And this random number is quite useful in many physical processes, and it is also uh, the basis of our cryptographic QKD protocols. So generalizing these results of this concept of measurement, as we have n qubit state, and we could get x the probability of getting x outcome by taking this inner product of state vector x with psi and taking its modulus square. So uh, we could generalize the concept of this simple measurement to multiple qubit states. So in today's lecture, we explored essential foundational concepts in quantum information that paved the way for understanding QKD. We discussed multiple qubits and how quantum states combine using the tensor product, enabling us to describe more complex systems like entanglement. We also touched on quantum measurements, understanding how information is extracted from quantum states and why the act of measurement is fundamentally different in the quantum world. These concepts are crucial for understanding the mechanics of QKD protocols, where we work with multiple qubit systems and perform measurements to establish secure communication. So, thank you for joining me today. If you found this lecture helpful, don't forget to like, comment, and subscribe. Feel free to share your questions or topics you would like me to cover in the comment section.